you everyone for returning promptly. So we'll same format as the previous session. This time the presentation is by my colleague from Durham University, Julian Williams. One of his co-authors, Fabio Misaki, is also here. I believe Chan Namango wasn't able to make it.
No.
So obviously this is going to give another perspective from a research point of view, but I think from what I've seen, this is going to again demonstrate the value of talking across the silo walls. That'll be my theme. Same rules, so it's 35 minutes, and I'll warn you when there's 10 minutes to go.
Super. Well, thanks very much for inviting me. Thanks for Alistair for organising this event. Richard, who's behind the left. It's a real pleasure to be able to give this talk, and it's a real pleasure to follow Peter, because many years ago when I started on my research career and kayaks was building up, it was one of those things where you say, wow, what a wonderful new piece of technology that came in and revolutionized how we do equity markets. And so if somebody like Peter Randall is saying that this is an important thing to do, then I think we all have to sit up and take notice. I am wearing jeans, and I don't have an earring, but I am going to talk about practical Byzantine fault tolerance and payment transactions networks. Don't worry, the title is a lot worse than the rest of the talk. My co-author is a computing scientist. I'm a professor of accounting and finance at the University of Durham. They hate the title. They really dislike it. I love the title, just because it has Byzantine in it. I just think it's kind of cool. But they tell me that this is a very old thing, going back to the 1980s, and it's sort of like, from a finance point of view, it'd be like saying revisiting the Black Skulls or revisiting the capital asset pricing models. I'm going to talk briefly about a very brief chat, because Peter has done a really good job of giving the background. And in fact, there are many, many things that Peter mentioned in the previous talk which are actually, sort of impact what I'm going to discuss. So I'll talk a little bit about traditional payment transaction networks. I have slightly simpler pictures than Peter, but they cover exactly the same points. I'm going to talk a little bit about high-level features of payment transaction networks, what's there, but then a little bit about distributed transaction clearing, a little bit about RTGS, which we obviously spoke about before. And then I'm going to talk about some new things, distributed execution of derivatives contracts as programs. This is something that I think is really interesting. And when I first started investigating blockchains, and we first started talking about it with the computing science guys, we felt, okay, where is the area for some expansion of research? And if you sort of look at it, then people like Settle have already, and Ripple and Hyperledger, have already really kind of looked at and done the economics on the domain of where blockchains can go in terms of providing simulated or synthetic ways of doing settlement that can replace existing transaction network systems. And I think that previous talk actually gave a really good understanding of the true state of the art. So I'm going to do a little tiny bit of futurology. I want to emphasize that I believe that everything that I'm going to talk about here is going to be conducted by financial services firms in general. I'm not going for some kind of sort of very communitarian thing where when we go out for coffee, we're going to be exchanging bitcoins through some kind of weird system. So therefore, everybody has to be part of a ledger. Each individual person's iPhone is part of a node and things like that. So it's important to remember that we're going to be thinking about this as mostly being driven by relatively large enterprises that are providing significant amounts of computational capacity to these things. So this is just sort of a brief list. The slides will be available. I put in quite a long appendix of slides because I appreciate the paper when I gave it to Philip was a little bit dense and has a lot of actual sort of bits of computer code and stuff like that in it. So it's not so easy to read, and so the slides give you a sort of an overview. So if you happen to be interested in something, then it's a good thing to have the slides available, and you can look at the appendix, which gives more detail. So if I skip over details, I apologize in advance. They'll hopefully be in the appendix. If they're not in the appendix, they'll certainly be in the paper. So I'll just click on from that. So I guess my most important job today is to stop you from, like my co-author is, tapping on the computer and actually listen and say, why should I be interested in this thing that I'm actually, I've given my time over for? And what we're interested in really is distributed databases. What we're interested in is transaction ledgers that are distributed across a large number of nodes. And what we're really interested in is when will it work, when will it break, and how can somebody extract or defraud it? And it turns out that actually, oddly enough, as with most things, we have quite a lot of already well-developed mathematics that actually describes most of these processes. So it's not a question of us sitting down and inventing new maths. It's more of a question of us sort of re-engineering what's already available and to do that. And I think the previous talk by Settle has actually shown a lot of this. And so one of the things that was interesting there was that they talked about 51% consensus. I heard that get dropped into the discussion. And hopefully, if you haven't understood what that said in that first talk, by the time you finish this talk, 51% consensus will make perfect clarity and perfect sense to you. And you can see why that would be a perfectly good thing to have should there certain characteristics of the network be, have a certain structure. So this is what we want. Alice emphasized to me in a very long email saying that I needed to make sure that I talked about industry, academia, policy making interface. So I hope I'm going to be able to talk a little bit about that. And obviously that's going to be dependent on how quick the cards come up. So Byzantine fault tolerance problem. I was told about this a while ago, and it took me a long time to sort of inculcate the idea of it. And the first sort of Byzantine generals problem was, long time previously discussed as a sort of game theoretic exercise. And effectively, you have the following idealized scenario. You have the Byzantine army. It's sitting outside an enemy city. It's got lots of divisions. Each division has got its own general in it. And some of those generals are drunks. They're incompetent. Some of those generals are loyal and competent, and some of those generals are actually defectors and they're malicious. And the objective of the Byzantine agreement is that all of the divisions should act in unison. They should either attack in unison or they should retreat in unison. What they mustn't do is do things in a piecemeal fashion. And it turns out that solving the Byzantine generals problem is sometimes very easy, sometimes incredibly easy, and sometimes is extremely difficult and requires very smart mathematicians like Philip and Fabio to really sit down and do some fairly sophisticated logic. And so that is basically it. It's about consistency and it's about agreement. And as Peter so amply demonstrated earlier on, agreement is everything. If we can have a ledger for which there is full agreement across the board at any given stage, that if you or I query the ledger, say, what was this transaction? How does this transaction work? How did it run? If we get the same answer at the same time, then things are working nicely. If we start to get different answers at different times, there's two issues there. One, things might be broken. Okay, that's fine. It's a fault. Okay, this is why we call it a fault tolerance problem. But more importantly than that, we can start to think about ways in which we could actually manipulate the ledger, and we could actually use it to create excess returns and excess money for us. We can defraud the ledger. And so that's basically the sum total of it. And I'm not going to talk too much about the maths. I'll give you a little bit of a brief overview. Some of the things that come out of it. But the point I'd like to say to sort of people here is that if you're interested in this and you're developing technology, obviously the first thing you need to talk to your technologists about is how am I generating agreement? And you'll see that different approaches to distributed ledgers, cryptocurrencies, and blockchains have vaguely different styles, but more or less they all collapse back to either the Byzantine fault tolerance problem or a brother of it or a sister of it. Now, I should, just before I start to go into it, I'd like to sort of pay tribute to a lady called Barbara Liskov, who is the Turing Award winner mathematician, who is the lady who has basically driven this. You'll see a lot of reference to Castro et al. That's a bit of a shame because she's obviously L, and so she doesn't actually appear in it, but she's the lady who ran the group that actually generated the practical Byzantine fault tolerance, which is the one that we often see today for lots of different cases. So I'm a financial economist, sort of like Alistair, more or less. Maybe sort of a mathematical finance guy, or you're more of a sort of general financial economist. So I'm not somebody who knows much about computing science. And I read Landport's original paper on BFT, and I found it easy to read. And I read, Barbara Liskov and Castro's paper, and I also found it easy to read. Believe me, it's one of the few areas where you can read a paper and you will actually get it relatively quickly. You don't need to spend vast amounts of brain power to understand what they're talking about here. There's no really complicated bits of logic, no technical formulas. You can read it. There is some math in there, but it actually tells you a lot about how you can structure a system to have certain fault tolerances allowing for it. I'm not going to go too much over traditional banking models. The reason being is that Peter did a much better job than I could ever possibly do in terms of describing how different bank models work. I think basically if you take Peter's slide and you sort of pivot his slide round and squish it up a bit, then basically my next two pickies are more or less the right and left side of Peter's previous slides. So there's very little point in replicating what has already gone before, but it's exactly what Peter said. Traditionally, how we've done things is that a bank, for example, Bank A or Bank B, have had the authority to transfer money between them, and they can do that on behalf of sub-banks, which may be not part of the system, for example, such as BACS, and those banks might be then channeling up transactions from individuals that can be much further down the layers of these different banking structures. So you could have somebody who's directly banking with Bank B, and they're changing their ledger in Bank A, and of course this is just simply B central bank A, and it clicks through. Alternatively, you could have Bank E, which is not part of the chain, and they're pushing transactions through. They have to go through Bank B, who goes through the central clearing system, through RTGS, and then that comes through to Bank A, Bank C, and you can see that at each individual stage, each of these arrows represents a transaction. Of course, every time you have an arrow, what do you have? You have a cost. And Peter, as I said, very ably demonstrated what the costs are. So if we could actually thin out these arrows, or in fact get rid of them, then we'd actually save ourselves some money. The other thing about it, of course, is that if we invest in a blockchain, there's no reason why the blockchain, as Peter very clearly mentioned, can't run all the time. And that's the big advantage of why blockchains seem like a revolutionary thing. Peter, you weren't in the room beforehand, but I said some very nice things about your job work on kayaks, so you can just pop in. So I wanted to say that. Correspondent bank models. This is effectively when you have foreign exchange transactions, and when you have foreign exchange transactions, you're going to want to have to go through some kind of market system, which is going to be clearing a spot rate in the currency exchange, and you have to have some sort of mechanism for clearing it. I called it an exchange here. That's going to be a bit of a misnomer because you could obviously have peer-to-peer OTC type market systems. And so effectively what you have is some kind of market makers in here who are actually facilitating liquidity. And of course the facilitation of liquidity, no matter what the structure of the system is going to be, needs to be given some kind of reward for. And as Peter has mentioned in the previous talk, and as we've seen in all of the other major innovations in financial services over the last 10 years, when the liquidity provision is provided in kind, things work. Okay? If liquidity provision is provided out of kind, things don't work. What do I mean by that? Well, if we had liquidity provision in terms of a blockchain, if we had units of a blockchain shifting around where the liquidity provision is deducted and added by the electronic currency that's sitting in there, things work nicely. And I believe that's where the settled system comes from. If you had it so that there was some separate account and some separate ledger where there was money being added up and deducted, things tend to work less well, okay? Because liquidity providers can be tempted to shift liquidity in and then shift liquidity out. But if everything is in kind, then they actually have to pay a liquidity cost to shift their money out. So they're always prepared to actually keep liquidity within the market, and that's an important aspect of when we shift over to, I say when we shift over to blockchain. There's not a question of if we shift over to blockchain, it's going to be when. Now, as I said, whether it's this sort of communitarian, everybody on the internet provides bits of the blockchain nodes, being very unlikely, much more likely that it's going to be provided for by the financial services in some particular way, or by technology vendors and some combination thereof. So, this is something where, we can replicate it with blockchains, and it can be effectively replicated, and the margins will be there because, it's a distributed system. We know that distributed systems work very well. Just to give you some idea of how much distributed systems work, one of the famous distributed databasing systems, which is not a blockchain or has anything like that, is run by, it's called Cassandra. It's a database that's run by Apple. Any idea how many nodes Apple has for its Cassandra database? Quite famous. No? Anybody from one of the competitor companies of IBM know how many nodes they've got in their Cassandra database? Anybody care to give a guess, just a number off the top of their heads? Give me a number.
1 million?
Oh, come on, this is like very high. No, they have 100,000. They have 100,000 nodes on their Cassandra database, and it facilitates a lot of their architecture for things like Siri, distributing these sorts of things. So there are big distributed databases in existence out there. IBM runs another one that's very large. Facebook runs a big one. These ones are distributed systems where there's a database, it's fragmented across many nodes, and the database is updated, and there needs to be some kind of fault tolerance attached to the updating so that there's consensus. So that we know if I'm buying my iTunes, my son, he loves Star Wars, so I'm buying my Star Wars cartoon for my son, that it's updated across the entire ledger, that is actually attached to me once I buy it. And that's part of what Apple does when it has some of its accounts. And so these kinds of things exist. They're not something that's crazy. They're not people with earrings and beards who are kind of like there. This is actually a real thing, and it can be made to work. And obviously the only reason why you wouldn't make it work is because you want to keep your rent. If you actually want to maintain your rent as the members of the points in here. So and Peter thought answered the question very nicely about why could you get this? Well, as soon as you start making this part very cheap, you create a competitive pressure, and then once you hit the point where people are going below their margin, so the blockchain is much, much cheaper, then first of all you erode their profit, then you go into their margin, then they start making losses, and at that point people have to shift over. And so there should be some kind of pressure at this point, and that's going to be an interesting case. Now, in the early 2000s, again, when I started to be an academic, we talked a lot about electronic communication networks for trading and transactions. And so this became a very important part of how we went about delivering things like securities exchange and various other cases. And they could be sort of like as simple as just payment systems, or they could actually shift out to something more complicated, such as things like kayaks and what we've actually seen the evolution of now, where we have sometimes centrally based or monolithic exchanges where we're actually trading securities like equities or bonds and things like this. And I thought it was interesting that Peter mentioned bonds as the first starting point, and I think bonds is obviously the place where you start, because bonds is the simplest security. Okay, it's a security whereby a coupon payment is made, and so it has an algorithm that's not state contingent. And as soon as you have something that's not state contingent, perfectly valid for a blockchainization, shall we say. So there's a kind of shift. We know electronic communications networks are popular. We know that people want to use them because of the ability to have uptime, the ability to actually create liquidity and use things and create economic activity. And what we can do is that we can start to replace the back end with a mechanism which is going to be distributed that settles in real time, and it settles quickly, and it doesn't have so many blocks in it. So, cryptocurrency. So in our paper, we tried to do a relatively comprehensive review of different cryptocurrencies. Now, why start with cryptocurrencies? Well, they were obviously some of the first major uptakers of blockchain type technology. One of the things I want to emphasize about this talk is the decomposition of the engineering of these things, and in the sense of we have a lot of discussion about the crypto aspect of it, or part of the cryptographic aspect of it is proof of effort. Well, Peter very nicely in his earlier talk said, well, proof of effort? I just need, fiat currency. I just need to say it exists. I exchanged it from the Bank of England. They distributed my ledger, and now I paid the money in. I don't need to have the proof of effort. The cryptographic protocol is just to make sure that it's a unique unique item on the actual blockchain itself. However, earlier ones were the kind of ma and pa operations whereby people were actually designing things which were supposed to be just distributed amongst friends, or in the case of Bitcoin, is exploded outwards. And what these are supposed to do is that they want to have some kind of proof of effort to show that it has value. Okay? We have mostly in the Western society fiat currencies, and I apologize to the financial economists there. When one of the things I thought was really nice in Peter's talk was exchangeability. Okay, so previously when we had a gold standard or a silver standard, why do we call it a pound? Well, it used to be that it was exchangeable to sterling silver. Now, of course, that doesn't happen anymore. We don't have an exchangeability to sterling silver. We simply have an exchangeability to an account the Bank of England holds on behalf of a bank. And so that's a very different proof of effort in terms of how it works relative to a cryptocurrency, where there has to be some kind of computation cost to say, this was expensive to make, and therefore it has value. Now I'm going to transfer that value along the blockchain, and that's how we're going to do it. And the blockchain is exactly as Peter mentioned. It's simply a way of transferring value up and down different people. But it's not a ledger per se. Okay? A ledger can be just any kind of database that holds information. It depends on who can write to the database and how that data is recorded. So these are all the different ones. I'm not sure if you all even know, but eCash 1982, the original of the original in terms of a sort of electronically tradable money, which had some proof of effort attached to it. As you shift down, you can see that these things are relatively new. 2008, Nakamoto. It's not Nakamoto, it's some guy in Sydney who's not the poor guy in San Francisco who was ambushed by reporters saying, you're the guy who invented it, and it turns out, no, he's just a guy who I think he was a baker. So, the hunt for Nakamoto's finished when the Australian authorities reported that they're investigating somebody for the amount of money that they had in bitcoins, and it turned out several hundred million, and quite likely that person happened to be the person who was the anonymous Nakamoto who invented these things. You have sort of an evolution of that, of course. My colleagues and I do a lot of work in information security, and we have the joyous task of watching Russian hackers. And Russian hackers do not use bitcoins. They use something else. What do they use?
It was called money something. I don't remember. It was from Russia.
Monero?
Is it? Pardon?
Monero?
Yes, I think it's that one. Yes, the Russian hackers don't use Bitcoin. They use an alternative one, which they've designed, but it's almost identical to Bitcoin in terms of its properties. And of course, anybody can script Bitcoin. Anybody in this room with the elementary ideas can build something, and then as long as there's a community to uptake it, you can make it. So, there are basically sort of like branches off of all of these things where somebody says, I don't like this Bitcoin aspect, so I'll just create something that's slightly different. So, lots of cryptocurrencies. Not so interesting for us, I don't think. Okay? I'll talk a little bit about Bitcoin because we spoke about it, but it's a proof of work. It has certain features to prevent overcrowding and denial of services. There's a digital signature, and it uses pseudonyms for privacy. Now, this is one of the reasons why I say that the Bitcoin model and the way in which Bitcoin works is not of any interest, I would have said to people in this room, because we don't need any of these things. The reason they wanted to invent this was they wanted to have anonymous money that was equivalent to the anonymity of cash. So I pass cash on around this room. It's not a question of I know precisely who had it beforehand. As long as I know at any given point when that money is spent, that that's the person who should have had that note, and that's it. The rest of the history is kind of irrelevant. So what they tried to do was build something that was equivalent to that, but of course it's electronic, so you could fork it. You could actually send it to different people. I could send one lot to Jonathan, one lot to Fabio. I could send one lot to Alistair simultaneously and say it's the same stuff. Well, this double spend feature needs to be corrected for. So how do we do that? Well, we need to have some way of saying the history of where I got the money from and how it's gone. So Bitcoin's introduced this idea of using the blockchain in this way, but anonymizing it. The blockchain becomes important for various different reasons, because it provides that certainty that the money that you have is the money that you should have. And so that's effectively where the blockchain comes from. I'm going to be relatively fast. And here's a blockchain, and here's a fork in the blockchain, and you can see that what we have here is the Genesis block, which has been created from the miners, and it shifts through, but we're actually looking backwards from the present owner. Now, the biggest problem that we have with something like a cryptocurrency like this is that we have the potential for forks. So what we have is that we've got 3 different lines in the blockchain which have all existed simultaneously, and we can see that this is actually quite a complicated line. And if we actually then go back to the consensus and then re-establish this is the dominant line, all the transactions that occur here get scrubbed. We've only really seen one massive fork in Bitcoin, but it caused a significant stir. We don't really know, because we haven't seen what's happened with the other smaller ones, but there's suspicions that certainly for some of the Russian hacker markets, that they've had massive forks, deliberately engineered by the people who are actually running them, and these forks have collapsed and caused all sorts of problems. So we want to be it's interesting to see how the black market has evolved in terms of using these things, so we can take some intuition from that, and we can just avoid their mistakes. So what about the alternatives? And I'll quickly shift through that. Well, other than Settle, which was the one that we spoke about, which is a much bigger project, this is a much more comprehensive way of doing things. There are things like Ripple and Ethereum, which are effectively cryptocurrency-esque, but then they take out certain things. So, for example, Ripple gets rid of the idea of having the proof of effort and uses effectively a gateway where a bank actually guarantees what the amount of money that comes in and out of the system. And Ethereum isn't actually even an active system. What Ethereum is a series of logical protocols that you can fit together to make the things that you're after. And I'll just sort of skip through these ones. This one's Ripple. And the most important thing you can see with Ripple is that you have gateways. You don't actually have the proof of effort coming in. And then internal to Ripple, you do your transactions. And then you can exit it by actually realizing your money through one of the given gateways. Of course, you are now subject to the liquidity of the gateways and the credit risk of the gateways. The credibility of the gateways is important. And then you can do Ripple for currency exchanges as well, more or less the same way. Ethereum, well, sorry again, Peter, it's Turing complete, and it has some arbitrary state functions, and it can be used to encode contracts. And I think Ethereum was probably where Peter's fire came from in the previous one, and I have perfect sympathy with him on that one. It's the idea of Ethereum as posited is basically it's the communitarian coinage system. It's going to have tens of thousands, millions, or even billions of people applying their Apple phone with it, and your Android phone, who's actually acting as the ledger. Is it going to be possible to run? But it's certainly Turing complete. So there we are. High-level functions of payment transaction networks. Well, again, just because of time, I'm going to skip through this one relatively fast. But these are the major features of the things that we need to have if we're going to build these things. There needs to be some way of creating the money, which is something that was talked about earlier, a promise, a realization, and storage. And the storage is the nebulous one, because of course, once we start to go to a fully blockchain-based or fully distributed ledger, then storage becomes an issue because there's a cost to storage. So you're not going to have a cost of liquidity, you're going to have a cost of storage. But from a regulatory point of view, how do you control the money supply? This is going to be the interesting thing. This is going to be something that's important for us. And I've got a few slides here which just give you some details on this, but it's not so interesting. I think Peter has talked about these in reasonable detail, and talk certainly about the central payment authority in much more detail than I have. What are the threats? Well, the threats are the standard threats we face in any electronic system. Subversion and faults. So what are subversion and faults going to do? Well, they can provide us with loss of value. They can provide us with information disclosures when we don't want them. And they can provide anonymity when we don't want anonymity. So if we want transparency, sometimes people can hide. If we want to have some kind of anonymity, it's important for us, and we're going to have practical threats. And these are the technological components that are critical. And again, this is more of a review for those of you who want to just have a quick catch-up on this. Decentralized agreement. And this is where our Byzantine fault tolerance becomes important, because we don't know yet how all of these things are going to be distributed. What hardware are they going to be sitting on? They're going to be sitting on the bank's own hardware, as in the settle system. This seems a very obvious way of going about it. Or are we going to have sort of virtual machines that are picking these things up? And I'm going to skip the maths. My last part is a bit of futurology in the last 5 minutes. I'm going to talk a little bit about smart contracts. And these were mentioned again by Peter earlier on. The obvious place to start when it comes to blockchain outside of simple payments is to go with something like a bond. Because a bond, as I said, is not dependent on state. What do I mean by state? I.e. how the markets are, how the universe is at a given time, okay, the alignment of the planets. It just pays a coupon. And the only thing that you know is that it pays the coupon on time, and does what it's supposed to do, or it's in default, and it doesn't actually pay it. And then it pays its settlement fine, its face value at the end. Okay? This is a program that can be executed and runs off. Okay? However, smart contracts are situations where things are state contingent. In other words, you need to actually feed information into the contract to actually understand how the contract is going to work out. And I think one of the really interesting points that was made in the previous talk was about OTC versus centralized clearing markets. Now, if we look at what the Dodd-Frank Act came in, 2010, it looked at the financial crisis and said to us, you know what, you guys didn't do a good job managing how these markets have developed. Okay? We had things like CDOs, as we mentioned before, and in CDOs, they were traded OTC. We had over-the-counter, which was just party to party, and we didn't have any real control over credit risk. And when we had cascade failures in credit risk, we ended up with things like the AIG bailout, and we ended up with sinks of risk, where one company had picked up lots of these contracts in the wrong position, and things had washed across. So Dodd-Frank says to us, central clearing rules. If we go to central clearing, then it's going to be expensive because the central clearing house is going to charge significant rents for that provision. It provides rents for two aspects of it. One is the provision of liquidity and indemnifying the individual parties against credit risk. And the second part is for providing the infrastructure. And so the idea of what we were talking about in the smart contracts, if you read the paper, is taking out the infrastructure part and actually making it a distributed ledger, which is executed. So when I say executed, what I mean is that the actual individual block itself is a program that needs to run, it collects some data, works out what state of the universe it's in, and then tells you what its value is. Now, that, I think, is an interesting area to go, and it's not something that we've interrogated to death yet. And so I think that's where the future lies as the logical progression from, first of all, let's deal with payment clearing systems, let's deal with RTGS. Now let's shift over to securities. The first types of securities are the obvious ones, but the more complex ones are going to be looking at smart contracts. And our current idea would be, for example, for cash settlement or physical settlement, that you would have a contract that effectively has some contingency based on some other valuations. And you have to separate off these two parts. One is liquidity provision, and the other one is the infrastructure provision. And then once you can separate these two things out, then you have quite an interesting play set for large firms. And so we do a lot of work with Chicago Mercantile Exchange. I fully appreciate that everybody here is from the City of London, but unfortunately CME tends to be the one that gives us some money. And so so we know a lot about things like the Globex trading platform. And so we're looking at Globex. What are the potential for allowing Globex to be built up? as a distributed ledger, which can then actually have bits and pieces of it run rather than in one big New Jersey site. Believe it or not, most of Globex is sitting in New Jersey, as well as a little bit of it in Chicago, simply because of the cost of actually putting a server in one place and the other. And so instead of having that kind of structure, actually dissociating it and actually building it into something which is a little bit more distributed and having a distributed ledger. And so that's more or less a little summary of the idea of smart contracts. And in the paper, what we've got is that we've got a protocol, just like the Nakamoto paper, in which we actually say, okay, if we have a protocol, how is the protocol actually going to be implemented? We implement it as a series of bindings, whereby the program has a binding relative to a state, and as the state evolves, the contract changes value. Of course, anytime you have a derivatives contract, you have to have margins, and you have to have some kind of way of managing credit risk, and we talk about that in reasonable detail in the paper, and I don't want to bore you with that too much now. Done. Yes, I think it's this is where where it's worthwhile finishing, and I think that the last point here is that the Dodd-Frank Act tells us a lot about how not to make an OTC market. And one of the objectives here strongly is to find a way of designing technology that can prevent some of the issues that happens when we have developments, unregulated developments of OTC markets. And I shall leave it there.
Thank you, Julian. So,